So today we are going to start flow through porous media. Whatever we have studied so far was in free medium or open medium when we just considered the fluid to be flowing within itself. But now we are going to consider porous medium where there are pores in solid materials, right? So solid materials will obviously does not allow the flow to happen, whereas there will be pores in between the solid material. There are gaps. In that gap, allow the fluid to flow through it, and that is why this medium is called porous media, because there are many pores in it. And in case of environmental flow, porous media flows play really important role, as you can consider this example of groundwater contamination, which is a very important environmental problem, because we know that a lot of contaminants are released from different sources into the groundwater, and that pollutes the groundwater. And if we want to find the quality of groundwater for drinking purpose, we must be able to predict the amount of contamination or amount of pollution. So to be able to study these kind of problems, we need to first understand how the flow in porous media happens in first place, right? So groundwater contamination is one of the problem, and not just contamination in general, the groundwater flow, right? It's not just the contamination that is related to the environment, but in general the flow of water in the ground, in soil or sand, that is an example of flow through porous media, right? And then if you consider few other examples where porous media flows are important in case of environmental applications, that counts geothermal energy recovery, where heat from the underground is harvested to heat the water, or to generate electricity, etc., right? So that is with the aim of getting green energy. Then seawater intrusion into groundwater, that is where in coastal regions the groundwater that you get is generally very salty, and that is because a lot of seawater, which is salty anyway, that intrudes into the groundwater and that mixes with it, and it makes it very salty. So again, to be able to predict the concentration of salt in groundwater, we need to be able to understand the porous media flow. Then there are other applications like underground storage of CO2 or hydrogen, natural gas, nuclear waste, etc. So these are all new applications where all these products are generally stored underground for different purposes. For example, carbon dioxide is stored for the purpose of mitigating global warming, or hydrogen is now stored to create green energy, right? And then natural gas or nuclear waste is stored underground to keep it safe from the surface level, right? And then also in case of petroleum industry, porous media flows really play a really important role, because the way all these petroleum products are extracted from underground happens only is possible only because of flow through porous media. So what you see here is porous media flows are really important in the environment, in nature, and we need to understand how the flow happens, and how do they affect all these environmental applications. And one thing which we have to consider is that in all cases before that we have studied so far in this course, we considered the flow to be turbulent, right? As I said, the flow was open or free medium, and that is why most of the flows actually happened with a lot of turbulence, where the effects of viscosity was minimal, it was very small. But in case of porous media, flow is primarily laminar. It happens very slowly because of lot of resistance the flow gets from the porous media, from the porous materials, right? And that is why the flow is mostly in laminar zone, and that actually means that the porous media flows have high effects of viscosity, right? And that's why effects of viscosity is very important in porous media flow, and we are going to consider that in our study in this chapter. So let's consider a flow through porous media, and we want to understand what does it actually depend on. So if you're trying to inject some fluid in porous media or there is a flow happening, that generally depends on three types of parameters. So first one is medium properties, which counts, for example, porosity, permeability, tortuosity, etc. We are going to see what these properties are. So that is the first type of property, right? That is medium property. And then the second type of properties are the fluid properties, the fluid that you are injecting, let it be water or any other liquid. So the density or viscosity of that fluid will be very important for this flow to happen. And then apart from these properties, these are, let's say, the inherent properties of the medium or the fluid. But for the flow to happen, you need to generate, or you need to provide an external force. In that case, let's say it's a pressure gradient between 2 points, right? So that pressure gradient between 2 points, that equally affects the flow through a porous media. Okay, so these are three different kind of parameters that actually decide what will be the rate of fluid transport, and what will be the direction of fluid transport, etc. Okay, so let's look into some of the properties which are very let's say common properties for a porous media, and then we will go into more details. So let's start with porosity. So porosity is defined as the fraction of interconnected pores in the medium. So as you can see in this example that is shown here, right, we are injecting a dark fluid here, in black color, and it is going only through this space which are open, right, which are connected with each other. So these are pore space, and what you see in the circles are basically the solid material. So flow happens only through the interconnected pores. It's not just the pore that is important, it's actually interconnectivity of the pore, right? If, let's say, there is a pore, but if that is blocked from all sides, if you consider these circular or spherical shapes that we have here, right, all these shapes, let's say if they are completely spherical, right, they are packed but is hollow inside, right, it's empty inside, that doesn't really affect the flow because that pore space inside is packed, and that does not allow the fluid to flow. And that is why when we define porosity for the flow, we talk about interconnectivity of the pores. Okay, and that is what defines the flow behavior. And that is why when we define porosity, we have to define it as the fraction of interconnected pores in the medium. Okay, and that is usually denoted by phi, and its value is between 0 and 1. Okay, so it must be greater than 0, otherwise it will not be called porous media, and it should be smaller than 1, because if it is 1, then that's again not a porous media, that's just a free media. Okay, and then permeability is another important parameter. So permeability is defined as a parameter that measures the ability of porous medium to transmit fluid through the pores, and actually it depends on the interconnectivity of the pores. Okay, so it's not just the pore that are important, but how easily those pores are able to transmit fluid through that particular medium, right? And that will depend on what kind of interconnectivity is there, because porosity will only give you the total fraction of interconnected pores, right? But it will not tell you the pattern of those interconnectivity. Let's say if the same medium has pores something like this, right, so they are just straight line, in that case that's also porous media, but in this case the flow will happen much more easily because it's just going in a straight direction, right? So in this case permeability will be much higher than the case that you see here, right? So permeability tells you the easiness of the flow in the medium, okay, for given porosity and other parameters. And these parameters, as we know, can only be found experimentally we cannot define it theoretically. So this must be measured experimentally, and based on that it can be characterized for a particular type of porous media. So these values, both porosity, permeability, are empirical values. They are not theoretical values for a medium. Okay. So now let's consider flow through a channel, or flow through a porous media, and we will try to derive a simple theory or simple law that will define the flow through a particular porous medium. So we will consider that there is this porous medium, which is, this is impermeable here, impermeable here. Okay, and this inside is all, these are all pore materials. Okay, so these are all pore materials, and now if you inject some fluid here, let's say that goes with a rate of Q, that is in meter cube per second, right? It will go through the pore space, right? So it will obviously follow many different paths, and at the outside again it will just come out as Q per meter cube per second. Okay, so the volume of fluid that was injected at the left must be coming out from the right. Okay, once the flow is fully developed, or the flow is in steady state condition. But now, on what all factors the rate Q will depend? Okay, so let's consider this is Q, and now we connected one manometer between these 2 points, point 1 and point 2. So here we read pressure is P1, here it is pressure P2. So we connect manometer or piezometer or some sort of pressure measuring device. Okay, and the length between these two is L, and the area between this gap is A, that is the area. And now if you want to measure the flow, this will actually depend on, so Q, which is the volume flow rate in meter cube per second, that will be a function of, that will depend on the pressure gradient. If there is larger pressure gradient, there will be more flow. Okay, so P1 minus P2, right? So because flow must happen from higher pressure to larger pressure, and that's why we are measuring it from P1 to P2. So P1 minus P2, it will also depend on the area. If larger the area, flow will be greater. If length is larger, then flow will be smaller, because it will have higher resistance. It will have to travel a longer distance, so you will need larger pressure for that to for that amount of fluid to happen, and that is why this is actually proportional to 1 over L, inversely proportional to the length. Longer the length, less flow will happen for the given pressure difference. Okay, and then we have the permeability of the medium. It will depend on permeability, where K is the permeability, which I forgot to define. So permeability is defined as K, and its unit is meter square. Okay, whereas phi is dimensionless. All right, so K is the permeability, and then obviously it will depend on phi, and it will also depend on the rho and viscosity. It will be inversely proportional to the viscosity of the fluid. So higher the viscosity, higher will be the resistance, and that's why less flow will occur if viscosity is very high. Okay, so based on this assumption, actually a scientist named Darcy, or engineer named Darcy, almost 200 years ago, he performed this experiment, and he found that this Q is proportional to delta P. So A times A over L times delta P, and is also inversely proportional to mu. Okay, so these are the parameters that it directly depends on, whereas the density and porosity will also affect, but not directly, and that we will see later how do they affect. But for now we will consider these four parameters and we will see how, where does this proportionality sign go. So here delta P that you see is actually defined, we will define it as P2 minus P1 because our flow is going from left to right, and generally the delta P is defined as next point minus previous point, right? So it has to be P2 minus P1, and if you call delta P by L, this can be defined as the pressure gradient. Right, and this value delta P that you see is negative because P2 is smaller than P1, right? And that's why delta P by delta L is also negative. Now we have seen that your volume flux is proportional to area and delta P by L, and inversely proportional to the viscosity, and there is this constant of proportionality, and that constant of proportionality, if you want to remove, that will become K A over mu delta P over L, okay, where K is the constant which is actually the permeability of the medium. Okay, and now if you divide Q by A, right, if you bring that the other side, that will give you the velocity of the flow. So Q is the volume flux, and if you divide that by area, that will give you velocity, right? So this is U K by mu dP by L, where U is the velocity, or you can call it fluid velocity. Okay, and if we assume L to be very small, let's say if L tends to 0, in that case this delta P by L can be actually approximated as dP by dx, right? If we consider extremely small length scale, we can simply convert this into differential form, and that is why this U can be given as minus K by mu dP by dx, where x is the direction of the flow, is the direction of the flow. Okay, and this equation that you get here is known as the Darcy's law. Okay, where the negative sign you see is because delta P is negative. Okay, delta P or dP by dx is actually negative, and that's why we have to use a negative sign here. In the permeability that we have seen, K is sometimes also defined as hydraulic conductivity. So this is hydraulic conductivity, which actually is given as K rho G by mu. Okay, where this larger K is the hydraulic conductivity and smaller K is the permeability. Okay, so now you see that the Darcy's law that we have written in form of permeability can also be written in form of hydraulic conductivity. If you convert this U into K over rho G dP by dx, this gives you Darcy's law in form of hydraulic conductivity. Okay, so this this is how the flow is also dependent on the density of the fluid, right? And not just the medium properties apart. Okay, so this is the Darcy's law what you have seen, and this is the more accepted form, and we are going to use this form for our analysis. But one thing we will see is that the Darcy's law that we have seen is not a universal form, and by that I mean it is not applicable in all conditions. Rather, it has several limitations. Okay, and one of the primary limitation is applicable only for low Reynolds number flows. Okay, so basically in this case Reynolds number is smaller than 10, then your Darcy's law is applicable. Okay, where Reynolds number in this case is usually defined as still rho u d over mu, where d is the pore length scale. Okay, so if Reynolds number is smaller than 10, then only Darcy's law is very well applicable, but it is not applicable beyond uh, Reynolds number 10. In that case, obviously, there are other forms of Darcy's law. For example, Darcy-Forchheimer equation, which is applicable when Darcy law is when Reynolds number is greater than 10. Okay, then other condition is applicable only for a steady flow. So here d by dt term is considered 0. So, and that is why we cannot apply it for unsteady flows in porous media. Again, you can use different modified form of Darcy's law, but not the actual Darcy's law. Okay, and then it is applicable for saturated medium only. Okay, so these are different conditions under which Darcy's law is applied. First, when Reynolds number is smaller than 1, that is the low Reynolds number flow or laminar flow, right? Then applicable for steady flows only, then that is where dy dt term is 0, and saturated medium only. Okay, but in most cases, we will consider these conditions anyway. We will consider laminar flow, we will consider steady flow, and saturated medium, and that is why we will be able to use Darcy's law for our case. Okay, so now let's see. Darcy's law is one of the equations, but obviously we need several other equations to be able to model or solve for a flow in porous media. And here you will notice that Darcy's law is a form of momentum conservation equation. Okay, this is equivalent of Navier-Stokes equation for porous media. Okay, so Darcy's law actually gives you the momentum conservation equation, and it is equivalent of Navier-Stokes equation. So we don't use Navier-Stokes equation in case of porous media. We rather use Darcy's law instead of Navier-Stokes equation. Okay, and that is why now we are going to define some governing equations for solving any fluid problem, and we will use Darcy's law as the momentum equation. So let's first start with mass balance, which basically is the continuity equation. Okay, so continuity equation will just work as it works in other case as well. So if you consider two-dimensional flow, it will work like this, or let's say three-dimensional flow. So it will be dw by dz equal to 0. Okay, that is the mass balance, that is the simple continuity equation, and it works perfectly fine. Then momentum balance, which basically is the Darcy's law. Okay, so here now we will write Darcy's law in three different directions individually. So u is in the x direction, and that is given as minus k by mu dp by dx minus rho g x. V is minus k by mu dp by dy minus rho g y, and let's say w is minus k by mu dp by dz minus rho g z. Okay, so these are the three different velocities in x, y, z direction. So u, v, w are the velocity in x, y, z directions, and g here is gx, gy, and zz. Okay, that is the gravity component. So when we talked about the gravity current, the flow here in a channel, we considered this to be horizontal, and that's why we did not consider the gravity component here in this equation, or in this equation. But if that flow is happening in vertical direction or with an inclined axis, in that case you will have to consider the gravity component. And that is why uh, if z is the vertical axis and x, y are the horizontal axis, in that case your u will simply be k by mu dp by dx, v will be k by mu dp by dy, and w will be k by mu dp by dz minus rho g. Okay, if z is vertical axis, vertically up. Okay, in this case your g will be 0 0 minus g, right? So it will be minus g in vertical direction, and that is how you define your vertical velocity and horizontal velocities as well. Okay, so these equations that you see are the three different equations, right? So this is equation a, equation c, and this is equation b. So these are the momentum balance in case of porous media. Okay, so mass balance, momentum balance. And now we can also quickly look into the third type of balance, that is the solute mass balance, which is also known as the solute transport equation or advection dispersion equation. Okay, so this is another equation that we use in case of porous media flows, and this equation is not just specific to porous media. This is something we have also seen before, and this is equivalent to energy equation for temperature, right? So here if we define C as the solute concentration, then this equation can be defined as dc by dt plus u dc by dx plus v dc by dy plus w dc by dz is equal to d by dx d dc by dx plus d b dc by dy plus d by dz d dc by dz. Okay, where d here is the dispersion coefficient, and d can be a function of x, y, z, and that is why we have kept it inside the derivative. Okay, but if the flow is only diffusion dependent, if there is only molecular diffusion happening, in that case d becomes equal to dm, that is the molecular diffusion coefficient. Okay, and in that case, or let's say not just molecular diffusion, but if d is constant, then this equation will simply become, let me copy this part first, equals d square by dx square plus d square by dy square plus d square by dz square of c, right? So basically you are double differentiating c with both x, y and z. Okay, so this is the solute transport equation for constant d. Okay, constant dispersion coefficient. So these are three set of equations which we usually use for porous media flow. So here the first equation obviously assumes that rho is constant. That's an assumption, right? And then that's why you are able to take rho outside the derivative. So this is a continuity equation. And then in case of momentum balance, we are using basically the Darcy's law, and that defines as velocity u, v and w depending on the pressure gradient in x, y and z direction, where the g is the gravity, and depending on how do you define your coordinates, you can get the value of g. Okay, and last equation is the solute transport equation, which is also known as the advection dispersion equation. Okay, and if your dispersion coefficient d is constant, if this is a constant, then you can use this equation, where if you want to make it little simplified, you can also put the c inside so that you don't get confused. So this is the same equation as we had written before. Okay, so now just one more thing that we have to understand is that the u, v, w we have defined are the Darcy velocity or the average velocity. These are not the actual velocity through the pores. Okay, so these are not the actual velocity. So actual velocity is generally defined as u prime, let's say that is the interstitial velocity as it is called, and that is given as u over phi. So this velocity that u with w that we have defined for the Darcy's law are the average velocity that goes through, we assume that flow is happening through complete cross-sectional area, right? And that is why we define this velocity for the complete area. But in reality, the flow is only happening through the pores, right? So that's why the velocity that you will see here we are defining as u, for example, and if there are a lot of pores, right? So this fluid will actually be going through these pores, right? So the velocity here will be u prime, which will actually be u over phi. So the amount of or the degree of increase in actual velocity from the average velocity will depend on the porosity, right? Interconnected pores. And that will define as the interstitial velocity or actual velocity within the pores. But we generally do not model for the interstitial velocity or the actual velocity. We generally care about the average velocity, and that is why even in Darcy's law you do not see the phi. Whereas if you want to define the actual velocity, let's say we had defined Darcy's law as k by mu dp by dx. If you want to write these in case of actual velocity, it will be phi times u prime minus k by mu dp by dx, and it will give you mu phi dp by dx. So this is the Darcy's law for interstitial velocity or actual velocity, right? But as I said, it is more complicated to consider interstitial velocity. Rather, it is easy to consider an average velocity through the medium, and that is why the other form of Darcy's law is more common, which we have used here, and as well as which we derived here. Okay, so this is the most common form of Darcy's law that we use. Okay, and this is without gravity, and if you consider gravity, then in all these forms that you see are applicable. Okay, so these are the basics of porous media flows, where we have seen different kind of equations, Darcy's law, continuity equation, and solute transport equation, whereas heat equation can also be defined for temperature, but we are probably not going to use heat equation in our course, and that's why I did not really write that. But a similar equation for temperature can be written like this. Okay, so in the next lecture we will see how to model the mixing behavior or a few other things in porous media.